So the differences between random assignment and random selection. Random assignment allows us to make inferences from our experiment, like cause and effect, which is what we want to be able to do when we're running an experiment. Random selection allows us to generalize results to a larger population. But the problem is this: you can't always have random selection. We need volunteers because we can't go out into the population and say, hey, I'm just going to pick you, especially because our volunteers have to meet our criteria for experimenting. Now, if you want to cover yourself and you want to assume the population is greater than 10 times the sample size, you're being safe on a prompt when you're really unsure about whether you are doing random assignment versus random selection. But keep in mind, when no sampling occurs, you don't really need to put anything about the oversampling issue. All right, so reading this next prompt, some things that I noticed is they did randomly select, and at the same time they randomly assigned, which would be important. I'm constructing and interpreting a 99% confidence interval for the average difference. So before I can get the average difference, I'm going to need to know the differences, and I have to make a decision about how I'm going to do the subtraction. So I'm going to do the regular minus the express. And you could do it the other way around. Your results will look slightly different, but that's still perfectly fine. So now that I have the differences, I need to look at the average difference, which means I'm going to need to put this into my calculator in a list, and then I'll do the summary statistics on it doing 1-bar stats. So go ahead, get those numbers in, and then do your 1-bar stats so you have that information to work with. So check your numbers and see if you got the same values that I got. Otherwise, go back and check it in your calculator. And so now, of course, I want to, since I have such a small sample size, I'm going to need to look at the graph of my data. So I'm going to, since I already have it in my calculator, I'm going to go look at a box plot, and I'm going to look at the normal probability plot, because as I'm checking the conditions, I have to see if it's normal, and those are the ways that I'm going to test. So go draw those on your paper, both your box plot and your normal probability plot. Okay, so checking all the conditions, I noted this earlier that they did randomly select times of the week, so an SRS was used. They also randomly assigned to the lanes each time, which would be important. And I can assume that the population of times that I might go would be greater than or equal to 150. And then the normality, I noticed that the box plot is a bit right skewed, but there were no outliers since I used a modified box plot. And the normal probability plot, although it had a little bit of skewness, possibly, I again didn't notice any outliers. So therefore, we may proceed. And we'll talk a little bit more about why we can proceed when the sample size is so small after looking at graphs when we look at robust, which is in the next box. So now I'm ready to actually do the calculation, which will look like this. And notice that I have my formula with all my numbers plugged in as evidence. And then, of course, I did use the calculator. And since I had the actual data set in, I used data on list 3 because I put those differences in list 3. And I had the hamsters actually generate the numbers. And then I can actually go back and just write this stuff down after I do all that. I will still have to look up T-star on my own. Okay, so then the interpretation piece, remember I have to interpret the interval, would of course look something like this. I could say the option B, which is 99% of all samples will capture the true mean difference in time between regular and express lanes to be between negative 21.91 and 107.25 seconds. Okay, so let's talk about robustness and why I can actually use these graphs as opposed to central limit theorem. So robustness is when the probability calculations are still accurate even when we violate a condition. So when the data sets are small, we can look at the graphs, just like I did above, and look at a box plot or stem plot, and the normal probability plot. And remember, we're looking for skewness on box plot and stem plot, and we're looking for linearity on normal probability plot. So then I have 3 different n values and the breakdown for what I would be looking for. So if n is less than 15, as long as it looks approximately normal, we can use t. If it's greater than or equal to 15 but less than 30, I can use t as long as it's not strongly skewed and there's no outliers. Remember, outliers are the devil in statistics. But if n is greater than or equal to 30, then certainly by our central limit theorem, we'll be able to use t even if it looks strongly skewed. And so finally, the last question is I want to be able to calculate a confidence interval. But the problem is, as I read through this, it looks like some stuff is missing. So I have my confidence level. Ooh, I have margin of error of at most. So margin of error has to be less than or equal to 30. I know the standard deviation for the pilot study was 154. So now that's previous information. So we're going to treat that as sigma because somebody else has done some study and that's what they're saying that the standard deviation is. Of course, we're trying to find how many, so we're looking for n, and that's all we have. So now remember, my margin of error for means is t star, and then the standard deviation over the square root of n. And in this case, I want that to be less than or equal to 30. So now, since I don't know my n, there's no way I can go look up t because I wouldn't have the degrees of freedom. So in this case, we'll have to use the bottom of the table and look up 90% z star, which is 1.645. And so I didn't mean to do that. So I'll have 1.645. And then again, I know what I'm going to consider to be the population standard deviation. So that's the only thing I have to use. Again, this is an estimate anyways. And so then when I do some math magic on that, if I divide both sides by 1.645, I get 18.237. And then remember, technically, these two trade places. So I have 154 divided by 18.237 is now less than or equal to the square root of n, which gives me 8.44. And then I'll square root both sides. So I get n greater than or equal to 71.31. And remember, n has to be a whole number so it's going to have to be greater than or equal to 72. All right, that's all the notes for this chapter. I will see you back in class.